Okay, testing. 1, 2, 3, 1, 2, 3. All right, so today we're going to try something a little bit different, and we're going to go through all the homework problems. But it's going to be, we're not giving out whole answers here, but we're talking about the problems enough to hopefully get you to understand things faster and or better than you would have understood them yourself otherwise. I like talking a lot about physical intuition for one, and I'm hoping that sheds a lot more light on these problems than maybe students are typically used to thinking about for themselves. But anyways, yeah, the session will be recorded, so let's get started. Okay, so the very first problem talks about a large meteorite skipping across, there's a lot of background, skipping across the atmosphere at some given mass and some given speed. And I don't really like the wording of this problem so much because it uses the word calculate the meteorite's loss of energy, which to me sounds really, really strange because the word loss is usually used to denote losses to friction or drag. But what it means by loss here is if this is the Earth, oops. Oh, come on now. My screen freezes up every now and then. Oh, wait a minute. Maybe I'm just using the wrong color. Oh, there we go. Okay, so if this is the Earth and a meteorite is coming in, right? As it explodes, it's essentially saying that all the kinetic energy is going to turn into, right? It's going to spatter out into a bunch of particles. All the kinetic energy that it had just before the moment of impact is going to turn into explosive energy, so to speak. And the question is just a really long-winded way of asking you what the heck the kinetic energy is right before impact. So that's just 1/2 mv squared, right? It's just the most simple equation. It's just a big exercise and challenging wording. All right, so if you're asked to express the energy as a multiple of the explosive energy of 1 megaton of TNT, well, you just take whatever that energy from part 1 was going to be in joules, and then you just divide it by, so if that's in, if part 1 you had the energy in joules, you just multiply that by whatever conversion ratio it is, 10 to the 15th joules, right? It's all an exercise in conversion, and I'll probably let you figure out part C yourself, where you're just being asked to figure it out in terms of the Hiroshima bombs instead, right? And that conversion rate is kilotons of TNT to 1 Hiroshima bomb. So yeah, let you take care of that yourself. We're gonna go pretty fast for these kind of conceptual questions. Anyways, for the next one, we're talking about an explosion at ground level leaves a diameter that is proportional. So I'm going to use some constant k, constant proportionality, equal to k e to the 1/3, right? Raised to the 1/3 power. Energy, the explosion raised to the 1/3 power gives you diameter. An explosion of 1 megaton of TNT leaves a crater of 1 km diameter. Okay, so it's like 1 km is equal to k times 1 megaton of TNT raised to the 1/3. So then you're basically just, it's going to end up coming down to finding some fraction, right? What was the kinetic energy equivalent associated with that impact in terms of, okay, so some other thing is found with a 46 kilometer diameter. Excuse me. Diameter proportional to the energy raised to the 1/3. Okay, so 46 kilometers is equal to k times, what is this? I guess we'll call it x to the 1/3. So basically you can just divide top and bottom, right? You treat this basically as a ratio. So 1 km over 46 km is equal to, well, the k's just cancel out and you're left with 1 to the 1/3 over x to the 1/3. So basically just solve for x. All right, and that kind of makes sense. It's basically like saying if the diameter increases 46-fold, you're going to find that I think you'd expect to find that the energy has to increase by a lot more than 46-fold because of the 1/3 power. Right? So, okay. And then the second part is just asking you to put it in terms of Hiroshima bomb equivalents. So that's just some unit conversion. You can figure that out. All right. So for the next one, I guess that's question 3. You're told some mass m moving along a wire in the positive direction, okay? So it's moving along the positive direction. So at t is equal to 0, the bead passes through x is equal to 0 with initial speed, some given initial speed, and a constant force acts on it, and it appears to be that the constant force is acting in the negative direction, right? That you kind of infer that from the fact that at t1, 1 second, 2 second, and 3 second, it sort of gets closer and closer together until it stops at t3. But the idea is, from this information, you can figure out what the acceleration is by using vf squared minus v naught squared. Maybe we'll call it v1 squared minus v naught squared is equal to minus 2a delta x, where the delta x is going to be the total travel here. v1, we're told that it's at rest at this point, right? Or maybe I'll call it v3 instead. Call it v3. v3 is equal to 0, and then the total delta x is just equal to whatever it is from the graph. Just read off that distance. So this will let you solve for a. So now we know the acceleration. And okay, now they ask you, what is the kinetic energy of the bead at t is equal to 11 seconds? Well, just use kinematics, right? Or use kinematics, figure out how much extra time is. Remember, a couple of seconds have already elapsed, and now they ask you at about 11 seconds. So basically figure out what v4 is equal to, what, like t4 minus t3 times a, and you should be golden. And keep in mind that acceleration is going to be negative, right? It's facing to the left, so make sure to add in a negative sign, because I solved it for positive over here. So it's positive over here, so add in the negative sign to indicate that it's going to the left. All right. So, all right, we keep going. So the next one says that, okay. We have some forces, F3, at some angle theta 3, F2, at some angle theta 2, and F1 going perfectly to the left, negative direction. Okay, so they give you the magnitudes of all the forces, F1, F2, and F3. And the indicated angles are also given. Okay, that's great. So far, so good. What is the work done by the canister on the three forces during the first 4.5 meters, or however many meters of displacement? Okay, so with this in mind, what you're basically just going to do is you're going to figure out what F net is. Yeah? Just figure out what F net is by, do you know the I and J notation? Just figure out the, F in the X direction, and F in the Y direction. Yeah? And you can do that just by breaking down these components, adding up in the X direction, adding up in the Y direction correspondingly to get F total in X, F total in Y. Use the Pythagorean theorem to figure out what the magnitude of F net is, right? It's just going to be, well, it's the Pythagorean theorem. You can figure that out yourself. Yeah, once you figure out what this is, at that point, you just multiply that by the displacement. And they give it to you. So remember, work is equal to, for a constant force, force times the displacement. Yeah, with this problem, you're going to have to do a little bit of cosines and sines, right? Because this breaks down into a F3 cosine theta 3, F3 sine theta 3, and similarly for this one over here. But keep in mind that it's the angle from over here now, right? It's the angle from the y-axis rather than the angle from the x-axis. So you just got to be careful about your sines and cosines. Just double check everything and work that out. All right, we keep going. So the next one is asking about, oh, wow, it's a very steep slope. So basically the idea is this thing is sort of like moving downwards by some distance, I guess, d. We know the angle theta, and we know that there's some force pulling on it. And the idea is, even though it's working downwards, right, it's sort of like the person doing the pulling over here is doing some work on the system, which means that the kinetic energy is different than if he wasn't doing that work. Yeah? And in particular, are we told that, excuse me. Okay, so we know the angle theta, we know the magnitude of the force, we know that the block slides down some distance, 0.5. Do we know the weight of the thing? We do not know the weight of the thing. Its kinetic energy increases by 80. Yeah, so, okay, if we don't know the weight of the thing, that means we can't... Yeah, we can't really speak to anything about the potential energy, right? It doesn't really matter. The potential energy for this problem, you know, it exists. It is presumably under gravity, and the gravity is presumably what moves it downwards. But they're asking us how much greater would its kinetic energy have been if the rope had not been attached to the block, right? So in the situations where there's kinetic energy and no kinetic energy, well, in both cases, there was potential energy. So, you know, the comparison between the two situations doesn't really matter. I'm sorry, why am I saying? There's the force or no force, right? So the potential energy, the potential energy change over a distance d would have been the same either way. It's only the kinetic energy that would have been different, and they're telling us that it differs in these two situations by like some number of joules, right? So this is basically saying that, sorry, this is very long-winded. This is basically saying that work is going to be responsible for the for whatever the change in kinetic energy from situation 1 to situation 2 is going to be, right? This is not delta kinetic energy, you know, delta over two different times, but it's rather the whatever the you know, it's the amount that the kinetic energy would have been greater by. Yeah. So basically, sorry, this is a really long-winded way of saying we're basically being asked to find the work for this problem. And once we figured all that out, well, okay, then at that point, it shouldn't be too complicated because you can just use work is equal to force times distance. And keep in mind that you should be, you know, this is sort of the dot product indicating the direction, or you can rewrite this as FD cosine theta. But the issue at play here is basically that the force and the displacement here are in opposite directions. So you kind of need to have a negative sign. Right, this thing is basically doing negative work, which is to say that it made the kinetic energy smaller than it otherwise would have been. But your final answer would need to be positive. Okay. Yeah, because it's asking how much the kinetic energy would have been greater by. Yeah. Let's see. If I'm not mistaken, I think that the angle for this problem is kind of a red herring, right? I think all you really need to do is figure out what force times displacement is, and the rest of the information, really doesn't matter so much. Yeah, let me know if that helps. Ice line sound for force that has a magnitude. Okay. Let's see. I feel like I'm making a silly mistake almost. But all right, let's keep going. Right, so the next one talks about some sort of, what problem are we on? 1, 2, 3, 4, 5, 6. I think we're on problem 6. So the next one's talking about a cave rescue team injures an injured splunker. Right, the lift is performed in 3 stages. So I guess in stage 1, right, it sort of goes upwards at with some acceleration a. Let's call it a1. And then in the second part, it's constant speed. So acceleration is equal to 0. And in the third phase, let's call it a3, is some negative number. Let's maybe call it negative a3, right? Because they're decelerating. But However, the work done by the force, right? The work done by, this is not net force, but this is rather the force that's being required to push him upwards. So F1, F2, and F3 are all going to be positive. These are the applied forces that are pushing against gravity, right? So in this particular situation, F1 is winning out against gravity. So it's winning out in magnitude against gravity. F2, it's exactly equal to gravity. And in F3, it's going to be, I think, less than gravity because it's decelerating. But that's being said, all of these are going to be positive because it's still... Yeah. Well, actually, that's not entirely true. It's possible that the last one... The cable lift is performed in 3 stages, each requiring a vertical distance. The initial stationary splunker is accelerated to speed. Finally, he is decelerated to 0 speed. How much work is done by... This is actually really funny, because the last one is kind of ambiguous. Each requiring a vertical distance of 7.2. Yeah. Anyways, these 2 parts should be pretty easy, because you can just figure out F is equal to ma, right? So F1 minus G is equal to ma. And you know M, you know A, you know G, so you can solve for F1. And then you can multiply that by D. And similarly for F2, you can get that F2 minus G is equal to 0. Right? And then, of course, I already said that F2 is equal to G. So then you can just do F2 times that distance. For F3, it tells that you were decelerated to 0 speed over 7.2 meters. So how do I put it? You need to figure out what his velocity is at this stage. He is then lifted at a constant speed of 1.1. Oh, I'm sorry, it gives it to you. So velocity right here is 1.1. So then we use Vf squared minus V naught squared is equal to 2a delta x. So it says that he's at rest at the end. V naught is the 1.1 or whatever they give us. And I guess the acceleration is negative. Maybe let's write it like this. And we know the delta x as well, so you can solve for acceleration. And then you can do F3 minus G is equal to, mass times that negative acceleration. And depending on whether, solve for F3, and depending on whether your answer is positive or negative, that means that, okay, if it's positive but smaller than G, that means that, it's still trying to push you upwards, and it's just, losing against gravity. But it could also be negative, in which case it's helping gravity to slow you down, right? But the reason that this matters is because the sign of F3 matters for the work as well, because, work is equal to sort of force times distance. And if they're in opposite directions, the sign's got to be negative, right? So just check your signs for that one. Okay, let's keep going. I want to get these done faster. All right, this next one is about a pulley problem. I think this is number 7. This one I had some people asking me about, and I think there's a kind of hacky, kind of incorrect way to do it, frankly. So the idea here is x1, x2. So if this is being pulled up with some tension T, right? So if you know the height h of this thing, and you know what x1 and x2 are, the tension in the cord is some constant that you know. Okay, so you know tension. So basically, some people were trying to argue that you could take... Some people were trying to argue that you could just take tension yeah, sorry. Some people were trying to tell me that you could, you could just take tension and multiply that by this distance and subtract it by tension multiply this distance. And it turns out that that answer is correct. But the reason why it works is, as far as I can tell, it's more or less luck. Here's what you really have to do, right? Your displacement is in this direction. Let's call that your dx, maybe. Your displacement is in that direction. And work is equal to integral of f. We're going to call it dx, right? And the fact that dx is going in the negative direction, I'm going to represent by the bounds of this integral later, but just bear with me for a second. So it's f dot dx, actually. which means that we basically have to figure out the angle theta between them. But the issue is that this angle theta changes as time goes along, right? It's going to be small out here, and it's going to be larger out here. And basically the issue is theta depends on x, right? So if this is equal to f cosine theta dx, you got to rewrite theta in terms of x. And it's okay, we can do that in terms of Pythagorean theorem, right? That's just going to be, if this is cosine theta, is going to be x divided by this hypotenuse, which is x squared plus h squared. So this turns into f x over h squared plus x squared dx. And that bound is going to go from x1 to x2. And you can do this integral for yourself. I recommend using u substitution. Let u is equal to x squared plus h squared. And make sure to really handle your chain rule carefully and all that. But yeah, this should bring you to the solution necessary. You can check mathematically for yourself that this works out to be the same as the solution that some students suggested. But as far as I can tell, it's just coincidence. Yeah, it's a neat trick though. Right. Okay. All right. So we continue for 8. So it's saying that initial object of mass m horizontally and uniformly accelerates. Okay. And so there's been BF during a time interval of length t. So how much work is done on the object by the force accelerating it? Well, we know that work is equal to the change in the kinetic energy, right? Like I kind of like to think of maybe kinetic and potential energies as like a bank accounts. Like one is a savings account and one is a checking account. Like forget interest, right? They're just two separate bank accounts that you can sort of move money in between them as you please. But in order to actually increase your total amount of money, you've got to have work come in from the outside. So in this problem, if potential energy doesn't really exist and all that there is kinetic energy and outside, outside money coming in, this basically says the outside work coming into the system is just going to be equal to your change in kinetic energy. And if it's at rest initially, this just means that work is going to be equal to 1/2 m vf squared, right? Okay, maybe that's, but I only say this part because it allows us to talk about the next parts. But if you're being asked for the instantaneous power due to the force at the end of the interval, one common problem is people trying to just take p is equal to w and divide that by t. And because that's what it says in your equation formulas, right? But the issue here is this gives you the average power over that entire time interval, and what we're being asked to find is instantaneous power, so this isn't quite right. Instead, you basically need to take the derivative, dp over dt. dp over dt. Yeah, and I think that should, oh, excuse me, why am I running it like this? P is going to be equal to dw over dt, right? So you need to take, I think you need to take an integral. Excuse me, why am I saying integral? You need to take a derivative. What is the instantaneous power due to that force at the end of the interval? Okay, all right. Bf during a time interval of length t. Anyways, all right. For part C, if you're being asked for the instantaneous power due to that force at the end of the first half of the interval, it's basically saying, all right, what if you've got a different expression where instead of VF, you were asked about the velocity halfway through, right? So that's basically turns into like 1/2 m, I think. So if the acceleration is uniform, right, there's some constant a, then v is equal to at. So if the time is halved, then velocity is also halved, right? Because there's a linear relationship. So you're basically, it just turns into vf over 2 squared. And then I think you need to take the derivative with respect to time, and that should get you the desired power. All right, making okay time. All right, we keep going, all right? Keep on going. All right, so a coin slides over a frictionless plane across an xy plane. All right, so now I think we enter a new segment of questions, but it slides over a frictionless plane across an xy coordinate, from the origin to a point with xy coordinates. right? They're given to us. Let's call it like, I don't know, 2.9 or something. Well, a constant force acts on it. All right. So the force has magnitude 3.5 and is directed at a counterclockwise angle of something like 120. Right. So if that force looks kind of like that. So from the positive direction of the x-axis, how much force is being done? All right. So basically for a problem like this, you know the angle of force from the x-axis, and you also know, you can also figure out the angle of this thing, right? So yeah, for a problem like this, it's just going to be, I think, FD cosine of the angle between them, right? And you just have to figure out that angle between them by using angle subtraction. You see that? One of the things that you might find a little bit confusing about this problem is that, why is it going in this direction if there's a constant force acting on it? Well, there could be a number of explanations, right? There could be other forces acting on it so that the net travel direction is, in a straight line. It could also be the case that it's not necessarily moving in a straight line, right? It could be doing some other wacky thing, like, maybe having some curved path that ends up there. But for the purposes of this problem, I'm pretty sure that no matter what path it takes, the work is going to be the same. It's sort of like, I don't know, if you can imagine like some object like falling due to gravity, right? Let's say that it's like a bird or something, and it's, slightly injured, so it's still flapping around a little bit. Let's say it's flapping around, a little bit here and there, back and forth a little bit. The total work that gravity does on it is still going to be like mgh, because gravity doesn't really care about your like movements in other directions or whatnot. It only cares about your total displacement in that direction. And the same idea with this force, right? This force is kind of like our analog for gravity. It's just the straight thing pointing in that direction, constant, right? So even if you, move around a little bit in weird ways, all it cares about is its, is your sort of movement in its direction, so to speak. And that's accounted for by multiplying force by d cosine theta, where again, theta is the angle between them. All right, I hope that explanation makes intuitive sense. All right, so if we keep going, so now we have some box, it's got some angle phi, but we don't know the angle of the slope, and we have some force. So the basic idea is a constant force A of known magnitude is being applied, and it's sort of going upwards at constant speed. Okay. How much work is done on the box by the force when it has moved through a vertical distance of, let's call it h, right? They say h is like half a meter or something like that. And one of the things you might be really tempted to do is just try to use FD cosine theta like we've been doing in the past. But the issue is, even though they give us this angle theta, the issue is we don't know the angle of the ramp. Sorry, if this angle is called phi, let's call the angle of the ramp theta, which we do not know, unfortunately. So our usual calculation, FD cosine theta, or like FD times the cosine of the angle between them, isn't actually really going to help us, because I don't think we can really figure that out from the information given. Right? We know nothing about the angle of the path. So, okay, with that in mind, are we out of luck? Well, no, we have some alternative means to do it, right? We can use the fact that the kinetic energy is not changing, right? Because it's at constant speed, which means that the work done by the force is going to be equal to the change in just potential energy, right? And the potential energy is just mgh, which we can figure out. So yeah, I think that's basically, if I'm not mistaken, I think that's basically all there is to say about this one. They give you some extra information to kind of almost act as a red herring, I think is the gist here. But it's this force that's excuse me. Sorry, let me double think about this one for a moment. Yeah, sorry, I'm just worried a little bit about whether we need to include the force of gravity in this at all. No, I think this should be fine, right? Just Anyways, let me know if that is confusing at all. I feel like I'm having a brain fart moment here, but I think that's all you can do with this information, right? We don't know the angle of the ramp itself. We do know the angle of the force with respect to vertical, but that's, like I said, I think that's kind of a red herring. Yeah, we basically know that the force of gravity and the force of gravity in the parallel direction and the force applied cancel each other out because it's moving at constant speed. So I think all that's left to do is basically to attribute all this work done to, all this like change in potential to the work of the force. Yeah, let me know if that gets it. All right, we keep going. All right, so a spring and block are in the arrangement of the figure. All right, so if you're given that it's pulled out to like x is equal to some amount, like 4 cm, right? And that you're given that there's some energy, let's call it 350 force of newtons to hold it there, right? If you draw the free body diagram, that means that if the force of the spring is trying to pull backwards and you have to apply a force of 350 to do it there, this means that, well, this is when they're opposite and equal, right? So if F is equal to minus kx, if force of the spring is equal to minus kx, and the fact that force applied plus force spring is equal to 0, that means that you can figure out what k is because you know what x is, right? So basically it's going to say that, this force right here, what did I call it? F is newtons, is going to be equal to kx, right? And the minus sign went away because we had to subtract to the other side, and the minus signs cancel out. So we know that the displacement here is going to be, so we can solve for k. We can solve for k just fine. All right, so that's why they gave that our information about the first part. It lets us know a bit more information about the spring. Right? They didn't want to make it easy for us. They could have just given the k information outright, but they wanted to make us work for it a bit. All right, so the next part tells us x is equal to some other displacement, right? Like say 11 cm or something, it's just getting displaced further. And it's asking us how much work does the spring do on the block when the block moves from, I guess, if this is its rest position, which is 0, right? And there's some position positive 6. It's asking about from 6 to positive 3, and from 6 to minus 3, 6 to minus 6. So I guess I'll draw 11 out here, and minus 10. So 2 ways to do this problem, and it should be the same either way. One option is, okay, if it's asking how much work does the spring do on the block when it moves from, say, here to here, you can always use F, oops, why did that happen? Work is equal to F times, F dot distance, right? And again, you just have to be careful about the sign because in this particular case, the force is pulling it backwards towards equilibrium, and the displacement is also in that direction. So they're both a negative in the negative direction, so that cancels out and gives you positive work, right? It's basically saying the spring is stealing kinetic energy from the block and storing it into its own spring potential energy. Yeah, so that's sort of the idea. And you just gotta do this for every single phase, right? So if the first phase from 6 to 3, there's that contribution. For 6 to negative 3, there's 2 contributions, right? There's one where it's doing, I think it's there's one where it's doing work. I'm sorry, why did I say stealing? No, I'm sorry, it should be the other way around. It's rather the kinetic energy is sort of stealing energy from the spring, right? Where the spring is doing work by giving its energy to the kinetic energy. Sorry about that. That was a little bit confusing. But yeah, okay. In the next phase, all right, so it gets to 0, where the force is acting in this direction. But then when it goes from 0 to negative 3, the force is acting in the opposite direction, right? So the idea is the two of them, the dot product is going to be positive for this part when you do F dot D in this part, but it's going to be negative in this part. So you got to figure out what the total thing sums up to be. And similarly for future parts, right? You just have a different stopping point and keep in mind what the make sure to be careful about summing up your contributions and whether those contributions are positive or negative. But okay, that's one way to do it. The other way to do it is you could have done this entire problem by looking at energy instead. You could say that U of the spring we know is equal to 1/2 kx squared. Right? You can look in your textbook how this is derived. It's really not that hard. Shoot, is it minus kx squared? No, it should be positive kx squared, because the further out you go, right, the more potential energy you have. Yeah, more is stored in the spring. But the idea here is you could have just compared you could have just compared the the potential energy at all the different positions you're being asked to compare, and just take the difference in potential energy and say, well, that difference in potential energy is I guess equal to is equal and opposite to the change in kinetic energy, right? And you can figure out, you should be able to figure out the work that way. So if basically, let's write it out, right? It's going to be like delta U is equal to minus the change in kinetic energy, which I think is going to be equal to minus the work, something like that. Just think through your signs, right? If the spring from position 1 to position 2 is losing potential energy, that means it's giving that potential energy to the block, to its kinetic energy, and therefore doing work. So you can always just, do your math carefully, but also do a sanity check as to whether or not your answer makes sense, whether or not your signs make sense. All right, so the only force acting on a 3.2 kg body as it moves. Gosh, should really go faster. The only force acting on a 3.2 kg body as it moves along the positive x-axis as x component fx, I guess this is question 4, is equal to minus 7x newtons. And oh, what do you know? This looks exactly like the force of a spring, right? So that's going to let us know that potential is equal to 1/2 7, which is going to be our spring constant, x squared. So the velocity of the body at x is equal to 2. Okay, so the velocity of the body at some point is given. All right, so what is the velocity of the body at some other point? Okay, so what does this tell us? So if they tell us that, okay, so this looks like a spring, right? So if we have that, at some point, x naught, we have velocity v naught, right? We know that u at this position is equal to 1/2 7 x naught squared, just from the potential energy equation for a spring. And we know this is a spring just because of what this equation looks like, right? It might not literally be a spring, but it's going to be something that behaves just like a spring. Yeah. If you want me to justify this a little bit more, right? If f is equal to minus du dx, then u is going to be equal to minus the integral of f dx. So this just turns, that's where this comes from, right? That's how x turns into 1/2 x squared. And then there's a constant of integration, but we can set that equal to 0, because in physics we kind of get to choose. All right, anyways, back to our plan. But this is equal to potential energy. Sorry, this is the potential energy, right? And then kinetic energy is just equal to 1/2 m v naught squared. So if we're told what the initial velocity is, sorry, do we know the mass? Yes, we do know the mass. Okay, so this is basically means we know our u naught and k naught. So then if we're going to use the equation, conservation of energy equation, mu naught plus k naught is equal to mu1 plus k1. Yeah. So if you're told that there's some new position, x1 at about 5 meters, you can just take mu naught here and k naught here and plug those in. Remember, these are two perfectly good numbers that we know at this point. And then you can just plug in 1/2 times 7 times x1 squared plus 1/2 times m times v1 squared. And then at this point, you can just solve for V1, right? This is why conservation of energy is so useful. It basically says if you know, of these four things, mu naught, k naught, mu1, and k1, you can, if you know three of them, you can solve for the fourth, right? You can solve for the fourth. All right. So what is the velocity of the body at x is equal to 4 point? Okay. What positive value of x will the body have a velocity? Okay, so now it's saying, all right, for parts B, now it's saying, all right, a slightly different situation. If we, again, we know mu naught plus u naught and k naught is equal to u2 plus k2, right? Now it's asking us, let's say that we know 1/2 m v2 squared, right? It's giving us some velocity, and it's asking us to find 1/2 7 times x2 squared. So exact same situation as before. You know u naught, you know k naught from before, and you know this now, so just solve for x2. Easy as pie, right? Okay, we keep going. The force on a particle is given by F is equal to F naught times x over x naught minus 1, right? Okay, so we're given F naught, we're given x naught, sorry, we're given F naught, we're given x naught, and we're asked to find the work done by the force in moving the particle from 0 to 2. It's not. Okay. This is just an integral, right? This is just particle is moving directly along the x-axis. Yeah, this just inner work is equal to the integral of f dx. So just plug this in and integrate it from 0 to 2x naught. That's really all there is. I wonder if the answer will be neat. I haven't worked that one out myself. Yeah, should be simple enough, right? Hopefully. All right. So now the next one, 6, is kind of interesting. It's saying that a really heavy elevator is being pulled up maybe by like a pulley, like a motor system, and then it's also got a counterweight on the other side, right? So if this mass is like, you know, big M1, and this mass is like little M2, right? So that's M1 is greater than M2. It's sort of like saying this mass is doing, right? You know what a counterweight is, right? Like it's the fact that it's almost as heavy but not quite means that you can pull relatively easily to make this thing move up because this one is sort of carrying some of the weight, so to speak. All right, so you're told it travels upwards, you know, some delta y. You're given that, and you're given the delta t as well. So starting and ending at rest. Okay, so this is basically saying if it starts and ends at rest, delta k is equal to 0. But the potential energy situation is kind of strange, right? So the work in this situation is going to be equal to delta of the potential energy 1 for mass 1 plus delta potential 2 of mass 2, right? So the idea is that if this is, and I guess it's plus the work of the motor. I'm sorry. I'm tired. I'm getting fumbled. No, the work of the motor is equal to the sum of the two change in potentials. But yeah, this is just going to be mg delta y, right? Because this is going upwards, and then this one is going downwards. So I'm representing that with a minus sign, delta y. So this one is mass 1, and this one is mass 2. And the idea is sort of saying whatever the difference in, right, this one's gaining a bunch of potential energy, and this one's losing some, but not as much. It's basically saying whatever that different discrepancy is, it's got to be made up for by this motor that's, you know, turning on with electricity and spinning and powering that raise. Yeah. All right. Keep going, making good time. All right, so an ice boat is at rest on a frictionless frozen lake when suddenly a wind exerts some constant force. Okay, that's east. All right, let's just say that force is like 200 newtons or something. I try to solve most things symbolically or show you how to start things symbolically. But because the boat has some sail, it's saying that, okay, it instead glides at some angle theta, north of east. So yeah, this is a situation where there's no potential energy involved in this problem, so just work is equal to the change in kinetic energy. Yes? So, and that's just k final minus k initial, and because it was at rest, you know, everything is just going to be k final. So basically, if we can just figure out what work is using force times displacement times cosine theta, we're good. And yeah, just go ahead and do that, right? There's yeah, you know all the information at this point, so I think you can sort that out. And remember, just solve for 1/2. Oh, excuse me. No, you don't even need to solve for velocity. You can just leave it as kf. So you figure out what this is, and of course that's just equal to kf, and you're done. All right, the next part is like so many words. Something about BMI. Ugh, how terrible. All right, so calculating the BMI for the heavy person, the light person, that's pretty simple, right? Just use the formula they give you. Make sure to use mass 1, height 1 for patient 1, mass 2, height 2 for patient 2. Yeah? So, all right, which participant experiences the greater peak force from the plate? All right, so if they give you a graph that looks like force versus distance, right? Just look at it and see which one has the higher peak force. Right, so if this is the line for patient A and this line for patient B, like just look at it, right? What else can I say? Which one has the higher peak force? Right, which one has the higher maximum force? All right, so then which participant experiences the greater peak force? How much energy is absorbed by the plate and covering? Like basically how much work is done on the plate for participant D? Okay, so now it's asking how much work is done for these two people, right? And again, if work is just equal to integral of FDS, right? Because now it's the forces are not necessarily constant, so you have to integrate. And instead of ds, it's going to be like dd. This notation is kind of terrible. This d means like the differential that you see in calculus, and this d is just the like displacement. So yeah, this notation is terrible, but you know, it is what we got. So yeah, and remember, integral is just area under the graph. So this question is basically saying just find the area under the graph of A and of B. And B is just a tiny bit harder because you got to break it up into kind of two triangles and a rectangle. But that shouldn't be hard. But yeah, just figure out those areas under the graph, and that's going to be your work right there, respectively. All right. And then they're basically saying, all right, next part is take those works you found and divide that by the mass of the respective participants. And then I'll let you figure out the rest yourself. They're just going to be questions where you have to interpret who has the higher plate absorption. Do the results correlate higher plate absorption for higher BMI or lower BMI? I don't know. Just take whoever has the higher plate. Oh, wait, which one's plate absorption? Yeah, anyways, at this point it turns into like a exercise in reading comprehension, and I'm too tired to finish reading this, so figure that out yourselves. Right, it's just a little data problem at this point, not really physics anymore. Okay, we keep going. So I don't even know what problems these are, but it's like force is equal to cx minus 3x squared, or something like that. X in a particle, moves along an x-axis, c is a constant. At x is equal to 0, so at x is equal to 0, we know what the kinetic energy is. So let's call that k naught, right? And x is equal to 3, so let's call that x equal 3. Let's call that k1. So we know that as well. And you're basically being asked to find out what c is. Gosh, I'm really tired. Okay. So you're basically this is a situation where work is going to be equal to delta k, right? Is equal to k1 minus k naught. And work is, of course, equal to force integral of dx. So just take that cx minus 3x squared, plug it in and integrate from x is equal to 0 to 3. Yeah, should be a relatively basic integral. And then just set that equal to k1 minus k naught. So at that point, you should get something that looks like shouldn't be too bad. You should get something that looks like a cubic equation. Right, I think you're going to get something. Oh no, it's pretty simple. Yeah, it's I don't know, I feel like I should just let you do the rest yourself. Subtract it out and then do like, right, it turns into like cx squared minus x cubed, or cx squared over 2, I guess, and evaluate that from 0 to 3. And that's got to be equal to whatever k1 minus k0 is. And at this point, you can just plug in 3 and 0 for x's and solve for c, right? Gosh, this is a, hopefully relatively simple definite integral. All right, so for the next problem, it's talking about a car crash where, okay, if a person, this is not a very nice car, but it's basically saying that, why did I draw legs for wheels? Okay, so it's basically saying that there's a displacement where the car has a crumple zone of some distance d. So the human gets displaced by that similar distance d, right? And they say it's like half a meter. So if you know the mass of the driver as well, assume that the force on the driver of the seat is constant, use work energy to find the magnitude of the force if the initial speed of the car is. Okay, so it's basically saying there's no potential energy involved here. It's just basically all work being done by I guess the work done by the crash is equal to delta change in kinetic energy is equal to k final minus k initial. So k final is just going to be 0 because they come to a stop, but k initial is just comes from whatever their v initial is, right? 1/2 mass v naught squared, and make sure to convert your units to be consistent with each other. Yes. So what is the magnitude of the force during the crash? So then, on the other hand, this is just equal to Fd. So you basically set Fd is equal to 1/2 mv naught squared. You may have to do a little bit of, I guess, remember that force also is going to be in the left direction, whereas displacement is in the right. So Fd, I guess, is going to have a negative sign here. Yeah. I usually like representing my values as positive, like inherently positive, and then just put the negative sign out in front, but you can like incorporate the negative sign into the force itself if you so please. Yeah? Because this is going to match up with minus 1/2 mv naught squared, but basically just solve for f. So okay, you do that with 2 different speeds, and if the initial speed is multiplied by 2, what is the multiplying factor? Well, you can kind of see that if minus Fd is equal to this, you note that if f naught goes up by, a factor of 2, f has to go up by a factor of 2 squared because of the squared, right? So it's not a linear relationship. It's a, well, I'll let you figure out the rest for yourself, right? I kind of said it, but okay. Anyways, we keep going. I think that's, yeah. What is this now? I think this is the next week's homework, maybe? But it's saying that there's some like roller coaster looking thing. And I guess this is height h. This is height h. This is h over 2. And this is a, b, and c. And this is v naught. All right, you're given the mass. You're given v naught. You're given h. How much work does a gravitational force do from that point to point A? All right, so again, excuse me. Sorry, I just got really tired. How much work does a gravitational force do on the car from that point? All right, so if this is your starting point, it's basically saying, I don't know, how do you put it? Like, it's basically asking you what delta change of u is, but like negative, maybe? How much work does the gravitational force do on the car? Like, mathematically, I know how this works, but it's just hard explaining and coming up with explanations for the signs, right? Because, like, if these are the same heights, right, this should clue you in about how the gravitational potential energy is changing, if at all, right? You should be able to figure out just the gravitational potential energy change and correspondingly the work done by the gravitational potential energy should just be like the opposite. I think it's like work of the gravity is equal to minus like change in u of gravity, right? Because this is sort of like saying, if it loses, like let's say delta u is negative, like it loses potential energy, that means it's making the car go faster. So that's like doing work on the system by gravity. So that's like why the negative sign is there. But yeah, so it basically just comes down to looking at the heights, and I don't think there's too much more to say. If the gravitational potential energy of the Earth car system is taken to be 0 at C, then what is it at points B and A? Yeah, again, remember that excuse me. Remember that changing or gravitational, so if this is defined to be your 0 point, then this is just going to be, or just mgy is going to be your gravitational potential energy for any height y. So yeah, just figure out how h2, h over 2 and h play into this equation. You can just, right, it gives you your vertical height. I think there's not too much to say for this card to be problem, to be honest. Yeah, I think the velocity is actually kind of irrelevant for this problem. Anyways, all right, we keep going. So for problem 2, you basically have a book being dropped down to a friend who was at D, and your height is h. All right, so it asks, what is the speed of the book when it reaches your hands? And at this point in this course, you can solve it in 2 different ways. You could do this entire thing by kinematics, right? If you could do this with vf squared minus v naught squared is equal to minus 2a delta y, I guess, because you know acceleration, you know y, you know v naught is just 0, so you could figure it out this way. So that's method 1, or you could figure it out using energy at this point, where k naught squared excuse me, k naught plus mu naught is equal to k1 plus u1. And you know that the initial kinetic energy is 0 because it's initially at rest. You know, right, so if this is, you know, at time 0 and this is time 1, yeah, you can basically at this point just figure out what the change in potential energy is. So u0 minus mu1 is equal to k1. And, right, remember that mu0 is going to be, it's higher initially, so this one's larger than this one. But then this is just equal to 1/2 mv squared, right? So you can figure it out, and either way will give you the same answer, whether you find it here or here, right? So just solve for vf here. mu0 minus mu1 should be easy enough. All right, if we substitute a book with twice the mass, what would be its speed when it reaches her hands? Yeah, so it's an interesting question, right? You should see some cancellation. I'll give you a hint. You just work through this problem, and remember that there are mass terms inside here as well. Right, there are mass terms inside here as well. Yeah, I guess, you know, just mg delta h, right? Mg delta h is what this is. Sorry. I guess they gave it to you as d, is this entire thing. So then maybe just call h to be the height between the top of the building and where your friend is, right? So h is just equal to d minus, like, big D minus little d. But anyways, you should see some cancellation when you set mg delta h equal to 1/2 m vf squared. And you should note that when you double the mass of the book, or half the mass of the book, right? This is that famous thing when Newton, is it Newton or Newton back in the day, noticed that even though back in the day everyone expected heavier things to fall faster, that's not actually true, right? Unless there's air resistance. So yeah, remember your middle school science lessons as well, and see how it works out in the math, because you should see that VF does not end up depending on, or you should look at how it depends on M, basically. That's all I'll say. All right, so if instead the book were thrown down with initial speed, okay, all right. Well, in that case, K naught, okay, so for the last part, C, I guess, K naught plus U naught equal K1 plus U1. Well, the only difference is that this has K naught is non-zero. But other than that, the problem gets solved the exact same way. Right, so you do K naught is equal to 1/2 m v naught squared plus U naught minus mu1 is equal to K1. Right? and that's just equal to 1/2 m vf squared to solve for vf. And this should all be pretty straightforward, I hope. All right, so let's keep going. Okay, so this is one where it gets slightly tricky. We're given the mass of an object. We're getting that drops from height around 80 centimeters, and we know what the spring constant k is. So this is what it looks like, right? This is what the spring looks like, and we know this height h. So the issue here is it's not as straightforward as just setting the potential energy of, mgh equal to 1/2 kx squared, because the issue is it travels a little bit further, right? There's a little bit more potential energy to be excuse me. There's a little bit more potential energy to be squeezed out of this extra little displacement. Let's call this maybe h2, right? There's a little bit extra gravitational potential energy to be squeezed out here. But the gist of this is, how do I put it? You can basically just start like at t is equal to 1, or let's maybe call it let's call this situation t0, and when they just touch, it's t1, and when it gets to the very bottom of the depress, when it hits the bottom of this, or sorry, when the spring compresses its maximum, let's call it t2. And the insight here is you don't really need to care about t1 at all, right? That's going to be the moment where the kinetic energy is at its maximum, but you're not really worried about kinetic energy in this problem. So instead, just compare t0 and t2. So it's basically saying if energy is being conserved, right, that means delta, how do I want to express this? So if like energy of the system at 0 is equal to energy of the system at 2, and the energy of the system at 0 is basically just mgh plus mgh2. Yeah, let's define at the very bottom of the compression to be our 0 point for kinetic energy. So if that's equal to 1/2 m, and the compression is just h2 squared, right? You can just solve for h2 like that. Oh, sorry, it should be a k. 1/2 k h2 squared. And yeah, you can solve for h2, and that's basically all you need to do, right? So problems like this one are just a little bit tricky because you've got that extra little distance that seems unimportant at first, but it actually does matter, right? That's actually the crucial part of the problem. Anyways, now we keep going. So if you have a conservative force, F is equal to ax minus b, where x is in meters, a and b are positive constants, x in a particle moving in the x-axis, right? So the potential u associated with this force is assigned a value of 0. So u of 0 is equal to 0. So you write an expression for the potential energy associated with this force, right? So just to remind ourselves, F is equal to minus du dx. So u is going to be equal to the integral of minus f dx plus c. But I think you'll find that when you plug in the initial conditions, this c is going to be 0, I think. But yeah, so just to go ahead and integrate this thing and figure out that expression for yourself. And part B is asking what is the maximum positive value of this potential energy. So if if the force looks like ax minus b, right, that looks like, so force looks like something like this probably. Well, potential energy is going to look like, well, remember there's a minus sign and this x is going to turn into an x squared. So it's going to look something like this probably. It's going to look something like that, which means that it's going to have a maximum. And they're asserting that this value is going to be positive. So yeah, to figure this out, you can just take your expression for u in the previous problem and take the derivative of it, which is just, undoing what you did in part 1 basically, right? The derivative of u is just equal to the negative of force. And you set that to 0 to optimize, so it's going to happen when this expression is equal to 0. Of course, you could have skipped this by just realizing that whatever your expression for u is, the maximum of a parabola is going to happen at its vertex, which is just, I think, like minus b over 2a. This b and a are from the quadratic equation, it's not necessarily the same capital A and capital B of this problem. But yeah, one way or another, figure out what that vertex is, and you should be golden. Use calculus or use middle school math. Either way is fine. All right, we keep going. For question 5, oh, okay, we have this funny little graph here. All right, so for this thing, we have the UC, UT, UB, I guess, is the hump. And then mu A is the sort of valley here. And you're being told that it starts at the top of this hill, right? A particle is released at the point potential hill, okay, and it has some initial kinetic energy, so k naught is equal to something, and u naught is also equal to something we're given. So what is the speed of the particle at x is equal to 3.5? All right, so basically I think 3.5 is just right here in this little well right here. So you basically just, it's just the same old expressions you've seen before, where u naught plus k naught is equal to u1 plus k1, right? So you know what u naught and k naught are to begin with, and you can figure out what u1 is. That's just going to be the height of this well. So then you can solve for k1 and the velocity. And for part B, it's asking about the, it's asking about this point down here, when I think x is equal to like 6.5. But yeah, it's the exact same idea, right? It's u naught and k naught are the same. Now you're just looking for u1 and k1, where I guess u1 is equal to 0. u1 is equal, I think they're indicating that 0 is the very bottom here. And then just find what the velocity is by 1/2 mv squared. Solve for v1. All right, so now it talks about turning point, right? So if it goes to the right side, the idea is, think of it like a ball rolling, rolling up or down hills. But the idea is that if it has enough velocity, it'll go up, go up, go up, go up, right until its kinetic energy all runs out. Let's think about this in terms of like, almost like bank accounts, right? Kinetic energy, and if you think about kinetic energy and potential energy is like bank accounts, where you can sort of move funds from one bank account into the other, right? Going up and down the hill means that when your kinetic energy is very high, your funds for your potential energy account are very low. But vice versa, your potential energy can never go negative. So if you put it all in, if you climb the hill higher and higher and higher, you're going to expend more and more potential energy. It's going to be higher. Sorry, your potential energy is going to get higher and higher, right up until your potential kinetic energy turns to 0, at which point you stop, and then you're going to fall back down. Right? So this question is basically just telling you, given your u naught and k naught, right, consider putting everything in towards a potential energy. Consider putting everything in towards potential energy so that k1 is equal to 0. And at that point, you're basically going to figure out how high on this thing u1 is, right? And to do that, you might just have to do a little bit of, so you know what u1 is, just because you're going to be able to get a straight up number for it, like 15 or 16 or 17, right? But the question is asking you the x position of the turning point, right? The x position, I think. So you basically have to just do a little bit of interpolation, because this is like a straight line, right? Because if this value is like 7 and this value is 8, right? The start of the slope, the top of the slope. So like if the slope starts at 7 and ends at 8, you can basically just like linearly interpolate where it's got to be. So if the, if u1 is like 3/4 of the way up in this height, then you know that the x position's got to be at like 7 3/4, right? It just, that should be how, I think that should be reasonably intuitive. You can basically just set a ratio for how much the change has got to be. Yeah, again, if the potential energy is halfway up the height here, then it's also got to be like halfway in the horizontal distance as well. So that'd be like 7.5. Just figure out what the height's got to be based on this conservation of energy equation with k1 crossed out. And then from there, you can figure out the horizontal distance. And for part D, if it's going on the left side, it'll be the exact same thing, right? It'll probably stop somewhere along here, and you just got to figure out what that height's got to be. Yeah. If, however, it had more energy to begin with, right, like if it kept going here, it might just, you know, go off to negative infinity or something like that, or it just might keep going. You know, it's a pretty intuitive idea. Just if a ball is rolling on like some hills without friction, right? It's like you can either transfer your funds to kinetic energy or potential energy. They kind of can interchange freely. You're allowed to like switch money from one account to the other, but like you know, you can't go too high. You can only go as high, you know, as high as money you have, right? Yeah. Anyways, at the very bottom of the hills is when all the money is going to be put into like the kinetic energy bank account, and at the, you know, highs you can go when kinetic energy is 0 is when you put everything towards potential. I don't know if this is a good analogy. I hope so. All right, so a fake large cookie is sliding. Interesting. So it looks like it's a spring. Okay. So it has a kinetic energy, you know, of k naught as it passes through the equilibrium position. So as the cookie slides, a frictional force of, I guess, 8 newtons, or however many newtons acts on it. So force of friction. So, you know, as it goes, force of friction acts against it. All right, so how far will the cookie slide from the equilibrium position before momentarily coming to rest? All right, so for a question like this, you know the initial k naught, mu naught is going to be 0 because there's no potential energy at equilibrium. But then that's going to be equal to, what is it going to be? Okay, so the other endpoint is when k1 is going to be 0. When it gets to its stopping point is when the kinetic energy goes away, right? Plus u1 is the energy from the spring. But then there's also going to be some work that gets stolen from friction, right? Friction kind of steals some of it, so it takes up some positive work here, because it's sort of like, if this didn't exist, everything would be going towards the potential energy and it would get stretched further. But it, you know, it exists, so it's going to like divert the funds away a little bit, right? It's like the tax man coming in to take a little bit of money out of your account, right? When you try to switch everything from your kinetic energy account to your potential energy account, the tax man takes a bit out and puts it into his pocket. I don't know if this is a good analogy. But okay, so basically at this point, you know literally what k naught is. You're given a number for it, right? So then the potential energy is just 1/2 kx squared. And then you're just approximating the force of friction as like, sorry, you're approximating the work done by friction as like force of friction times the displacement. Sorry. Yeah, I realize this probably isn't the most satisfying explanation, because I know that the excuse me, the force of friction is pointed to the left, right? But the displacement is to the right. So that means that the work, I'm trying to say, the work done on the system by the force of friction is negative. But then I think like the other way around, like the amount of energy lost from the system is positive. Sorry, it's sometimes hard to track the sign, but like intuitively this should make sense, right? Why it's positive over here. Because it's kind of like stealing. Anyways, well, double check that and tell me if I'm stupid or if I'm wrong. You know, I'll say more on that maybe later if it needs to be said. But okay, and now it asks, what will be the kinetic energy of the cookie as it slides back to the equilibrium position? So, okay, right? So the issue is, because of the frictional force, it's not going to be exactly the same kinetic energy as it started. In fact, whatever this frictional, you know, work lost to friction is here, it's going to be doubled again because it passes, right? Because, excuse me. Right, because it gets to the most compressed point, and friction work, you know, stole some energy on the way there, but on the way back, it's going to be equal and opposite, I think. Yeah. We're more or less approximating friction as a constant force that just acts opposite of the motion. Gosh, why is the sign what it is? Am I just doing something really stupid here? Right, because work is equal to this is bothering me. Why am I off by a sign here? All right, so I'm going to draw another diagram. So, all right, this thing is moving inwards towards the spring, right? And force of friction is going to be dragging it backwards. So velocity is in this direction, displacement is also in this direction. So you'd think that work is equal to F times D done by friction would be negative. So that is to say that like E final yeah, what the hell? Why am I getting my signs mixed up? I must just be like sleepy or dumb. It's like work is equal to change in energy of the system. Right, so then 1/2, excuse me, minus FD is equal to 1/2 kx squared minus, so this is the final energy, and the initial energy is just k naught, right? Okay, so this does make sense, right? I guess I just sort of had my reasoning kind of reversed. Like I had it right. Like force friction D. Yeah. So I guess work is the negative force of friction, but you're sort of like subtracting it or subtracting a negative to the other side, which is why this is positive. But like you can also kind of like reason through it the way I did, where I said, okay, well, friction's being stolen, so it's going to be sort of a positive on the final right-hand side to indicate that it's being diverted, right? You can think about physics intuitively; it usually works. Anyways, that's sorry, long diversion about a very subtle, a very stupid question. Yeah. All right, so all right, next question is again a block sliding into a spring attached to a wall. All right, so you're told the mass, you're told the spring constant K, and you're told when the block stops. It has compressed the spring. Okay, so you know delta X at the end. So the coefficient of kinetic friction, you know what mu K is. When the block is in contact with the spring and being brought to rest, what is the work done by the spring force? Yeah, so work is just, in this particular case, is just going to be equal to the change in I guess the minus change in potential of the spring, right? Because if it's increasing in potential energy, like it's stealing energy for itself. So it's sort of like doing negative work on the block because it's making it move slower. So just figure out what change in potential energy of the spring is. And yeah, the rest of the problem should be clear from there, right? Because it's just asking for work, which is a negative of that. So then the increase in thermal energy of the brick floor system is going to be yeah, I was a little bit confused about this one, but I'm pretty sure, again, work is just going to be equal to, sorry, work done by friction is just going to be equal to friction times delta X. Yeah? What is the increase in thermal energy? Right? Yeah, work is equal to force of friction times delta X. And you can get this just by mu mg, right? So then for part C, this is basically the exact same equation we had in the previous problem, where k naught is equal to 1/2 kx squared plus force of friction times distance, except for distance, now it's delta x. So you can basically just use that exact same problem. Right, so delta U of the spring plus FFD, that would delta X. So then you can solve for kinetic energy, and from there you can find 1/2 mv squared, v naught squared. easy enough, right? Yeah, I'm getting exhausted. So many problems. All right, let's go ahead and wrap this up. All right, next question is this like little spiral thing, where this is R, and this is R, and that's H, I guess. And this is P. Yeah. So what's happening here is, what are the magnitudes A of the horizontal component? Right, so we know mass, we know loop R radius, we know that H is equal to 5R. So the idea behind this problem is that, okay, if it gets released, it's going to have, we can figure out what the velocity here is just by conservation of energy, right? Because if this is 5R and this is just R, there's going to be some difference of, the height difference is 4R, right? So just by, again, the same old equation, probably sick of it by now, but K0 plus U0 is equal to K1 plus U1. So all we know is that K0 is 0 because it's at rest initially. So then U0 minus mu1 is equal to K1. So this is just mg times the change in height, which is, I guess, like 4R, right? mg times 4R is equal to 1/2 mv1 squared. So you can solve for v1. And from there, you can go back to circular motion, where you know that F is equal to ma is equal to mv squared over r. It's going to be the exact same v that goes into here, right? So this is going to be F net in the horizontal direction, because at this particular point, the only force acting on it in the horizontal direction is normal force, right? Or like, you don't even have to think of it like that, right? The fact that it's moving in a horizontal, the fact that it's moving in a circle and is at the like rightmost point of the circle means that it has a, how do you put it? The centripetal acceleration is all horizontal, right? So F horizontal net is equal to the like force in the inwards direction, which is just equal to mv1 squared over r. So yeah, this is going to let you find F horizontal. All right. So for the next part, it's a little bit subtler. Oh, sorry. They also ask you for the vertical component of net force on the block at point Q. I don't know what else there is to say. It's just gravity, right? Like the only thing, the normal force is going inwards, and the only thing there's nothing else touching it. It's just gravity, right? So force of vertical, I think, is just equal to force of gravity at that particular point. Right, so the last part is, at what height h should the block... Okay, so now we're changing h to no longer be 5r, but we're contriving it so that it just loses contact at the top of this thing. Which, on the verge of losing contact, means that force normal... So if before you have force gravity and force normal, this is basically saying force normal is equal to 0. Maybe it would do good to talk about, like, intuitively what the heck this means. Like, if you're going really, really slow along this loop, you're not gonna make it to the top, right? You're gonna fall down. It's like that Simpsons movie thing where Homer is riding a motorcycle around the circle, around the sphere. But if you're going really, 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 really fast, right? mac is equal to mv squared over r is equal to, I guess, force normal minus force gravity. So at the very top, force normal minus force gravity is equal to mv squared over r, right? If you're going really, 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 really fast, like incredibly fast, force normal's got to be huge, right? And in the positive direction. So that's basically saying that if you're going really, really fast, you can, and you probably know this if you've ever been to like an amusement park in one of those like really extreme rides where it starts spinning. But right, the force normal is going to push you really, really into this contraption thing if you're going really fast. But if you're going slower and slower and slower and slower, I'm sorry, am I stupid? I'm sorry, wait, I'm so dumb. What happened here? I got my directions mixed up, right? Centripetal acceleration should be negative right now because it's downwards. Force normal is upwards, okay. Am I getting myself mixed? God, I'm so tired. All right, so what happens if you have incredibly high Oh, I'm sorry. This shouldn't be like sorry, what am I thinking right now? Anyways, let's figure out the math first, and then I'll try to think of how to explain it intuitively. So yeah, basically you're trying to get to the point where force normal is equal to 0, right? So get rid of force normal. So basically it means that Fg is equal to mv squared over r. So Fg, you have that, right? That's just mass times gravity, mv squared over r. The point is, this v will tell you what the kinetic energy at that time is, and you know the potential energy at that time because it's just based on the height, right? It's just twice the radius. And that's going to be equal to k naught, which again is 0, plus, because you're leaving from rest, plus mu naught, which is just mg times the new h, right? So basically the idea is solve for h here, given that you know k1 and u1. Yeah, I'm getting my signs all the way mixed up over there. Yeah, I'm trying to figure out an intuitive explanation here. And one of my signs is just wacky. So earlier when I said Fn minus Fg is equal to mv squared over r, right? Is that true? Or is there a negative sign here? Anyways, the point that I'm trying to make is that Fn can point, and Fg definitely points downwards, right? But Fn can either point upwards or it can point downwards, right? Like basically Fn can change depending on what your speed is, and it changes to accommodate this all. So what I'm seeing here is that, like, if Fn is just too high, it sounds like you're just not going to make it across this thing at all. I guess that's what it's saying. If Fn is too high, it's not going to... Why am I getting this so mixed up? Yeah, if Fn is too high, I guess you just sort of get stuck. Yeah, what am I saying? Why am I saying this? Oh, I'm sorry. I don't know why I kept thinking Fn was that way. I got messed up with a boomstick problem. No, it's a surface, right? So Fn should usually be pointing downwards. And the idea here is that, okay, Fn gets smaller and smaller. Like if Fn is massive, right? So this is minus Fn minus Fg is equal to minus, okay, now it makes sense. If Fn is absolutely huge, V squared gets huge as well, right? Because Fn can vary, V can vary, but Fg cannot. So this thing can be absolutely enormous. And that means if you're going around really, really fast, you're going to be, you're going to feel a ton of pressure from the wall, which I think makes sense. It hurts a heck of a lot, right? If you go fast enough, it presses you really hard. So then the idea is if you're not going quite as fast, then if Fn gets smaller, right? It gets smaller and smaller and smaller so that Fg is doing most of the work, right? And Fn can completely go away, but for this particular problem, it cannot change direction, I think. Yeah, for this particular problem, it's not going to change direction because just by the way this thing is structured, you're just not allowed to. Right? This thing can only press on you or not press on you, can't pull on you. But yeah, that's the motivation here for the relationship between Fn and V. So basically, when Fn gets the smallest possible, which is 0, V basically gets the smallest possible. And that's when you're just barely making it over the top. Anyway, sorry, that was really long-winded. All right, so we keep going, right? A spring force is a function of a stretch or compression. So it's saying that where spring for a gun is compressed by some like 4 meters according to the chart, and the chart will tell you what the heck the force versus X diagram looks like. All right, so if you know the mass of the cork, make sure to convert it to kilograms if need be. What is the speed of the cork if it is released as it passes its relaxed position? So, all right, so if initial delta x is equal to like -4, I guess. All right, because it's sort of going from its relaxed position is in the middle and it's going that way, right? Delta x is in the negative direction so that it goes that way. And then once it gets released, it shoots out that way. So that's pretty easy, right? That's just, again, we keep writing the same equation, but k0 plus u0 is equal to k1 plus u1. So here, k0 is 0 because it's at rest when it's compressed, and u1 is at 0 because there's no spring compression energy when it's at its equilibrium. So you just set 1/2 m delta x squared is equal to 1/2. Sorry, this should be a k as always. 1/2 m v squared. And the only like slightly challenging thing about this problem is that you don't get k right away. You have to figure out what k is from the graph. Yeah, you have to figure out what k is from the graph. And remember, if f is equal to minus kx, oh, look at them. It's kind of silly. They're considering this direction to be positive, right? They're considering the left direction to be positive and the right direction to be negative. It's very funny. But I digress. It doesn't matter because these values are squared anyways, so the signs don't matter. But anyway, the point that I'm trying to make here is, okay, f is equal to minus kx. So I guess this is the positive direction of... Okay, you know what? Their graph is just inconsistent. Don't think about it too hard, because they're also claiming that this is the positive. Yeah, okay. So if this is the positive direction of x in their graph, but this is the positive direction of x on the actual gun. So don't think about this too hard. But the point is, k is going to be the slope of the graph, right? You can get k just by looking at rise over run. So at that point, you know everything, so just solve for v. Sorry, that was kind of long-winded. But okay. At this point, it's saying that, okay, let's say it sticks for a little while before separation occurs. That's basically saying k0 plus u0. Well, k0 is still 0. It's still at rest at full compression. But they're saying k1 plus u1. So the idea here is it's going to be at its very fastest if it's released at this midway point, at this equilibrium point. But if it goes for a little bit longer, some of the energy is going to go back towards the potential energy of the spring. It sort of like steals the energy back a little bit. So this mu1 is no longer going to be 0. So okay, this just turns into 1/2 k of, I guess, like delta x naught squared, the full compression. It's equal to 1/2 m vf squared plus 1/2 k, and this is going to be delta x1 squared, like the new compression, the 1.5 centimeters or whatever. So just exact same idea, solve for vf. Solve for vf. That's all. All right, so for the next problem, this one's kind of interesting because it kind of requires a simplification. But the idea is you're sort of like pinning down this like chain here. Excuse me, I'm just going to draw this as a one-dimensional rope. But the idea is like you're sort of like pinning this thing down with your finger, right? Wow, that's a terrible finger. And the idea is, okay, if this total length is L, 1/3 of L is hanging off here. But what's kind of a little bit hard to know, so if you know the mass and you know the length, then you also know, let's call it lambda is equal to the linear density, which is just mass over L. Okay? So two ways to do this problem. So the issue here is basically saying, all right, how much work is required to pull the hang part back up to the table? That was just going to be equal to minus change in the potential, right? Or sorry, is it just going to be equal to the change in potential? So if initially the potential is kind of low because there are parts hanging below the surface level, and then you pull all of it up, the potential is going to increase and work is going to be, okay, it's going to be equal to the same sign as change in potential. So the idea is, okay, what's the change in potential? Well, we know that potential energy for point mass is mg delta h, right? For a point mass, but the issue here is it's not a point mass, it's sort of a linear thing. So what instead this is going to have to look like is delta u is equal to the integral of mg and like a tiny little displacement h. And in fact, instead of m, it's going to be lambda, because now it's going to be sort of linear density, right? You can think of this as like gravity times some little chunk of mass. Let me explain it this way. Gravity times a little chunk of mass times... Damn it, how do I explain this? All right, let me take a brief break. All right. All right, let me put it this way. So delta U is going to be equal to, so normally it was mgh for a point mass, right? Or the change in the height. So if this is what it's got to get up to, and there's just some chunk over here, we could maybe call this chunk like dh. Yeah. So the idea here is if this is dh, and it's also got to travel some height, some like height h, right? The amount of like change in potential that this little chunk experiences is going to be gravity times, let's call it like delta mass, like this delta means like a small chunk of mass times h, right? But delta m can be rewritten using the linear density thing as lambda times delta h. This basically means like the line density times a very, very small infinitesimal segment of it. And then in the notation of calculus, we just rewrite this as dh, right? This is dh. So then the idea is we integrate this thing from I guess minus 1/3 L to 0. So if we're setting this to be, if we're calling mu is equal to, actually, you know what? I don't know. What do you want to call the zero height? Let's say that this is when mu is equal to 0, right? So that's when y is equal to 0. So then we would integrate this from 0 to 1/3 L. Like, the thing I need to get across is you can have a lot of choice when defining which your 0 is in your coordinate axis or for your potential energy, right? I could have defined this as negative 1/3 L to 0, or I could have done it the other way around. But point is, this goes from 0 to 1/3 L, and this becomes, well, just do the integration, right? This is an integral with respect to h. Let me write h over here, lambda h. And just, yeah, this should be a pretty simple and straightforward integral. It's going to be a quadratic, right? But, okay, so that's the precise but kind of hard way of doing it, is to talk about integration. You could have done it another way, though. Yeah, I'm pretty sure that you could have done this problem just fine by treating it as a point mass halfway. And that only works because the density is linear. Right, so if you have this thing over here, you could have just approximated this thing as a point mass with 1/3 of the total mass of the rope at, I guess this is at height 1/6 L. Right, you could have just treated this as a point, as something going up like that. I think that would have worked just fine. But yeah, what do I know? What do I know? Yeah, does this all make sense in the end? I hope so. I hope so. So this thing only works because it happens to be linear. If, for example, this line density was like quadratic, right? Like one side, it gets denser and denser as it goes along, the length of it, this approximation is no longer going to work. I wouldn't necessarily say that it's coincidence or luck, because it has to do with the fact that it is linear, that this is allowed. But like the justification of why is, I think, a little hard to explain without calculus. How do I put it? Maybe the way to explain it It's just that it happens to work out really nicely because for every chunk here and for every chunk there, right, the average of these two, like for every corresponding two chunks that are equidistant from the center, like their average is going to be constantly, like the average amount of energy that they have to, how do I put it? For chunk 1 and chunk 2, like, you know, they're going to have some or some average potential energy they need to go upwards. And the idea is, as you like push this chunk closer and closer to the center, like correspondingly march them along, that average stays consistent. And this is the reason why it works out so nicely. Like if you've ever heard that story of like Gauss as a child figuring out that the sum of 1 plus 2 plus 3 ... plus 100 is equal to 100 times 101 over 2, right? The story goes that he did this in his head by figuring out this like nice little correspondence, plus 98 ... plus 1. Like he figured out that if he just wrote this sum in reverse and just started lining up corresponding terms like this, right? So you would get 1 in 100, which adds up to 101, and you would get 2 in 99, which adds up to 101, and 3 in 98, which, oh look, it adds up to 101, right? Like if you add all these numbers together this way, you would get 2 times 101 times, well, there's 100 pairs, right? So twice the sum is equal to this. So sum is equal to, sorry, where did I get this 2 from? I'm stupid. 101 times, yeah, excuse me. So that's, sorry, I'm having a moment here. Why am I doing so bad? Twice the sum is equal to 101 times 100, right? Because there's 100 of these 101s. Then sum is just equal to 101 times 100 over 2. It's kind of the exact same idea, right? That these little chunks are sort of paired just the same distance from the center, and they line up so that their total distance that they have to move is constant, like similar to 101. That's why it works, right? And this sum, if it was 1 plus 2 plus 3 plus 4, all the way up to 100 consecutive sums, this works great because it's like more or less linear. But if instead this was like 1, 4, 9, like all the squares, this would no longer have worked. Anyways, that's a really long-winded explanation. I hope that makes sense. All right, we keep going. God, I need to finish this faster so I can get to sleep. All right, so if we continue going, we have some mass sliding here, and there's some like spring. All right, so we know the mass, we know distance d down the incline, we know theta is equal to 26 degrees, where it runs into a spring of, okay, we know k as well. So it stops, it compressed the spring, so we know delta, I'm going to call it x, even though it's on an incline. All right, that's the spring compression. So what are the distance d and the distance between, all right, what are distance, okay, so it's trying to ask us distance d, which is, okay, so it's asking us to find d, which is how far the thing travels until it comes to a rest. Not when it makes contact, but until it comes to a rest momentarily. Yeah, so the point of maximum compression. And the idea here is, okay, now we need to start being really careful because wait, hold on. What are the distance d? Maybe I'm misreading this. Maybe d is just the distance until it meets the spring. The problem is kind of ambiguous. Down a frictionless incline where it runs into a spring d. When the block momentarily stops. Okay, so maybe it's saying distance d is where it just meets it, right? So, okay. Let's figure this out. God, I'm so tired. Okay, so like K1, K0 plus U0 is equal to K1 plus U1. And I'm going to say that K1 and U1 are when it totally stops at the end, okay? So the idea is it's going to compress some extra bit. Let's call that extra bit delta x. Right, and they give it to us, it's 16. But the idea is we need to like start looking at some trig here. You see what I mean? the idea here is that if this is a right triangle, right, it's going to have hypotenuse delta x plus d, and we know the angle theta. So this total distance traveled is delta x plus d, and we know the angle theta, but what I'm trying to find here is the height, right? So this is, right, this height h is what I'm interested in. So if sine theta is equal to h over delta x plus d, then we solve for h. So h is equal to delta x plus d sine theta. Okay, so the reason I wanted to find this was because it basically tells us the difference between our gravitational potential energies. Oh, sorry, I should have also mentioned that mu of spring at the full compression is going to be this equation, right? So your just initial kinetic is 0. Your final kinetic is also 0, I believe. And then u0 minus mu1 is going to be given to us by this h here, and then us, right? So what does this look like? This looks like u0 minus mu1 is equal to us 1/2 k delta x squared is equal to m times g times h, which we found over here. So just go plug that in, right? And then at that point, you can solve for d. Yeah. You know, d is inside h, so just solve for it. Solve for d. And that should be gravy. Right? It's just a little bit messy because you kind of have to figure out that both the delta x and the delta d are important. Sorry, delta x and d are important to finding the h, but it should be okay. All right, so the distance between the point of first... Okay, so part B is kind of interesting because it's a little bit unintuitive for just a minute, but it's basically saying, all right, after you make, you know, this thing speeding up, and making contact with this thing, right? For a moment, you might think that the moment it makes contact is its point of highest speed, but that's not actually true necessarily, because when this thing starts compressing during the early stages, it's not very strong at all, because remember, force is equal to minus kx, right? So what this is saying is that the force of gravity in the parallel direction is still going to beat out this force for at least a little while, which is to say that this thing is going to continue to pick up speed for a little bit, which means that its point of highest speed is actually going to be a little ways inwards. And this actually took me a moment to think about, but we're trying to optimize where we're trying to maximize VF, right? But because k is equal to 1/2 m VF squared, VF is going to be maximized when VF squared is going to be maximized. So we're kind of just maximizing k with respect to position x. You see what I'm saying? Gosh, I'm really tired. I keep saying that. I know. I'm just so tired. All right, so what are we trying to do now? So we're kind of reusing our equation from before. K0 is still 0 plus U0 is equal to K1 plus U1 plus US. So before, where delta x was given to us, now we kind of have to solve for it. Right, now we got to solve for it. So K0 is 0. U0 minus U1 is still the same expression, mgh. It's just now that it's just not going to be the same h as before because delta x is going to be an unknown value we're solving for. But that's going to be equal to K1, which is what we're trying to maximize, plus US. Just okay, so then this turns into mgh, or I'm going to rewrite h now as delta x plus d sine theta. All right, so that's that part. And then we're going to subtract out 1/2 k delta x squared. And that's going to be equal to K1. So at this point, I hope it should be clear. We're taking the derivative of everything here with respect to the delta x, the little displacement. So take that derivative and set it equal to 0 and solve for it to optimize. Or you can remember that this is just a quadratic, So the maximum is going to occur at the vertex. And that vertex you can find from middle school math. All right, so that's kind of a nifty little problem. It took me a little while to think, but not too bad, I hope. All right, next one. Keep saying I should go faster, but I'm just really tired at this point. But physics is fun, so I'll keep going. All right, so if the distance d is between this and the target, and there's some height h here, what's kind of curious about this problem is that they give you, there's a lot of unknowns that they just don't even mention. So part of the fun behind this problem is that a lot of things just cancel out or ended up not mattering. So okay, they tell you d, they don't tell you the height h. They do tell you that Bobby compresses the spring by delta x for Bobby is given, right? So what do we know? So we know, okay, let me put it this way. We know that no matter what the horizontal velocity at the point of launch is, vertical and horizontal velocities are independent, so it's going to take the same amount of time to fall down, right? It's going to take some time t, which we don't exactly know because we don't know the height in any case. So then the amount of travel time, horizontal travel time, is just going to be v naught times t, right? So basically this is your x position where it lands is going to be x is equal to v naught t, which is to say that x is going to be proportional to v naught, right? Because t is going to be, funny enough, t is going to be constant in this problem. For any launch you do, t is going to be the same value. So okay, the higher the x, the higher the v naught, the higher the x, right? Which means that if you know how far the first one landed, and you know that initial velocity, you just have to crank up that ratio enough to make it land where you want, right? So where did it land? I guess they said that Bobby missed it by like a little d or something. So this means that capital D minus little d, big D, has got to be equal to v naught, or I guess I'll call it like v Bobby. V Bobby over v, what's the other person's name? Rhonda? So this is what we want to find, and we can easily find that, right? Just solve for VR. Okay, so now we know what VR is. So, okay, if we know what VR is, or what VR rather needs to be, gosh, what else left is there to say? All right, so we also know how far Bobby, sorry, do we even know how far? My mistake, sorry, we don't actually know VB, so we can't quite solve for VR, but I just wanted to bring up this relation. Because it's going to be useful in a moment, right? Sorry, let me bring up my notes because I think I can explain it better from there. But I can always just wing it. The point that I want to get... Oh, shoot. Where'd I go? Anyways, the point that I want to get across here is we know that I'm not going to bother writing it out at this point, but 1/2 k of the initial delta x displacement, right? How much you compress the spring is equal to 1/2 m v naught squared. This is, the velocity of release. Yes. So this is to say that if you solve this out, it turns out that v naught and delta x are equal to each other. So, right, because what is this equal to say? No, they're not equal to each other, but they're linear to each other. Linear with respect to each other. So maybe the way to say this is, well, the bottom line that we're getting here is that delta x Bobby, there's got to be this ratio, delta x Rhonda, right? And at this point, we can solve it. But, this might make intuitive sense to you, or it might not. But, for those that do, great. You can finish the problem off by solving for delta xr, because you know delta xb, d minus t, and d. But if you need a little bit more justification, you can just kind of, well, it's not really not that crazy. You can just imagine isolating V naught, right? You can imagine isolating V naught, um, and just substituting in for VB and VR, right? So this, like, they each have an initial velocity from their launch. And then what you should find is that once you solve, like, okay, so the halves cancel out, V naught is equal to K over M times delta X squared. Right? You can square root everything, so square root everything. And then you can just plug this into VB and VR. Right? You can get that VB is equal to square root of K over M times delta X for Bobby, and V naught is equal to square root of K over M times delta X for Rhonda. And then just divide one by the other and see that VB and V naught are proportional to delta X, B, and delta X are. So yeah, at this point, just ignore the velocities and set these equal to each other and just solve for XR. All right. Oh gosh, yeah. So, all right, we're getting to the end here, but we're being told that, okay, this next problem is just some initial speed of 77.9 miles an hour, and then final speed of 82.9 feet a second. So you need to like check these units and convert them to match up with each other. And then you have to turn it into foot-pounds, which you need to maybe look up and figure out how to convert, or, you know, foot-pounds appears to be a unit of energy. But basically, this lets you find out K initial, and this lets you find out K final. And you can see that there's going to be a difference between them, right? So just take the difference, KF minus K naught, and convert that into foot-pounds, this really funny unit that they're insisting on. All right, so for the next one, you get this like little half-pipe looking thing. So you get the distance L. I guess this is supposed to be flat. Right, so this distance right here is L. This distance right here is H. It's how high the thing initially starts on. So it's frictionless for this area, but then has friction over here. So you can basically say that kinetic energy at this point 1 is equal to all the initial potential energy, right? Man, I get so tired of writing it out every time, but I think it's a good thing to do for consistency. U1 plus K1. So K naught is 0, and I guess you can just sort of do U naught minus U1 is just mgh, right? And that's equal to K1. So you can figure out you can solve for whatever the initial velocity here is. Mgh is equal to V squared, 1/2 mv squared. Oh, I'm sorry. The particle is released from point A, which is height h is equal to L over 2. Okay. Sure. Whatever. And it asks, once it starts going, there's going to be some force of friction is equal to, or they give you some like kinetic force of friction, right? So mu k mg, and then you just have to do force of friction times distance is equal to, yeah, I guess you didn't even need to do this if you didn't want to. But you could just plug in mgh here directly, right, and solve for distance. I was thinking of kinematics for a second, because then you could figure out what the velocity is once it starts in the friction area, and then figure out how long the force takes to die out. Sorry, how long it takes for the force to decelerate it. I'm sorry, I don't think you can actually even do that, because you don't have mass. Well, never mind then. Sorry, forget about that. Basically, just this is the kinetic initial energy you have, right? This is sort of like your bank account, and it's sort of saying like, all right, the tax man is sort of taking money out of your account at this rate, and they're told force of friction is how far they're sapping it out, so then you just multiply that by d and solve for d. That's how far out you're going to stop, right? So from the edge of a cliff, gosh, I really need All right. So you're told that you're launching this thing at some initial kinetic energy, and you also know its weight. It's question 8. So the projectile's maximum upward displacement is 170 meters. Okay, so to do this idea, so if it goes an extra basically 170, right, you can basically say k0 plus u0 is equal to k1 plus u1. And it sounds like it's saying that u1 minus u0 is going to be equal to mg times h, or 170. Yeah. So you know k0 and k1. So you can solve for k1 because at this point, you know that at its highest point, there's going to be no vertical velocity. So all of this is going to be horizontal velocity. So this is going to be 1/2 mv horizontal squared. Let's just solve for this and then solve for vh. Yeah. So then, okay, once you know, so the horizontal component does not change the entire time, right? The horizontal component is going to be just totally consistent, which means that the horizontal at the highest point is equal to the horizontal at the starting point. Okay, so if v squared overall is equal to vh squared plus v, the vertical at the initial velocity squared, right? Well, 1/2 m v naught squared is equal to 1/2 m this stuff squared. So just solve for vv now, because you know all of this. You figured out vh, and you know this stuff too, so solve for vv. That's going to be your vertical velocity. And then at the instant, the vertical component, all right, so now they're telling you something else. At the instant, the vertical, excuse me. So again, we know that for part C, we know that horizontal component is always constant. So, but vertical component of its velocity is 70 meters per second, which means that, you know, from the launch point, it's gone up by h is equal to 70. Well, again, we can use conservation of energy. I know you must be so tired of this by now. Equal to k1 plus mu1. And so k0, again, we know the initial thing. And k1 is what we're trying to... No, I'm sorry, we know k1 as well, because we know vh and we know vv. So we know what k1 is. So all we have to do is solve for mu1 minus mu0, k0 minus k1. So solve for this, and then, which is just equal to mgh, then solve for v, basically. That's all there is to say. You know, for this problem, one of the insightful things is basically that the horizontal component of velocity and the horizontal component of as far as and vertical component of velocity, because the Pythagorean theorem is like vx squared plus vy squared is equal to total v squared, it's sort of like saying the components of energy are compartmentalized into vx and vy like, even though energy is a scalar, it's sort of like saying the horizontal and vertical energies are sort of like independent of each other, right? Because it's like if this is v and there's a total kinetic energy, there's sort of like a vx and like a kinetic energy component from the x component, and a vy and a kinetic energy from the y component. And the idea is that v squared is equal to vy squared plus vx squared means that ke is equal to kex plus key. See how that works? Because 1/2 m v squared is equal to 1/2 m vx squared plus vy squared. Right, this is total energy. And this part, right, if you distribute it, you get kinetic energy in the x direction, kinetic energy responsible for the x direction, kinetic energy responsible for the y direction. And you can kind of see that the relationship between energy and the Pythagorean theorem, it all works together really nicely. Yeah? All right. Okay, we're getting to the end here. So we know that there's some mass for crates that are being dropped on a rotating belt. I should really get myself like a vertical treadmill. So what happens is the belt is moving some speed, and you have some friction coefficient. Great. So the idea is once it lands, it's going to be slipping for a short time, but then the belt grips it with some traction and starts moving it, right? So you basically just got to figure out what the change in kinetic energy supplied to the crate is. And that's just easier. That's just 1/2 mv squared. And then B, the magnitude. Yeah. Right? Because the initial velocity is 0. Vf is known because it's the speed of the conveyor belt. But V0 is not known, so yeah. Sorry, V0 is 0. So delta K is just equal to this thing. It's easy. So the magnitude of the kinetic frictional force acting on the crate, frictional force should just be equal to mu mg, right? Nothing to say for it. But yeah, energy supplied by the motor is actually kind of a weird question because I think it's just equal to delta K, because like the motor and friction are kind of one and the same in this problem, where the energy the motor is supplying sort of acts through the force of friction because the force of friction is accelerating the box. But it's just kind of like a weird statement, right? But anyways, I think the energy supplied by the motor should just be the same thing as the kinetic energy here. I hope that makes sense. Anyways, very last question. Yeah, I'll go to sleep. Yeah, so if you're told 0, 2, 4, 6, 8, 0, 2, 4, 6, 8, 10, and 12. Yeah, so you know that a conservative force is acting over some regions. So like F2 is only half this, and there's an F3, and an F4. Well, they tell you what directions these things are in. So, I don't know, this problem isn't very interesting. It's just a bunch of computation. The particle is released at x is equal to 5. Okay, that's there. With some given kinetic energy, not. And a potential energy of 0. So if it moves initially in the negative direction, you're being asked about what its k and u are at x is equal to 2. So as always, just use u0 plus k0, and this is 0, is equal to u1 plus k1. And, well, you can see that, well, maybe that's not the best way to explain it. X is equal to 2. Yeah, so if you have a conservative force, right, you have F is equal to, or I guess like U is equal to the integral of f dx, right? So basically the idea here is kind of just, because all the F's are, nice, they're, constant over the range they exist, this just turns into like minus F times the X over which they reside. But you also got to keep in mind the direction. I guess we'll just maybe call this F times delta X. But you also got to keep in mind that if their F and delta X are in opposite directions, you have to add another minus sign. So yeah, basically just use this to figure out what the change in potential energy is going to be. And because it's a conservative force and I guess energy is being conserved, you'd expect, you'd expect any any gain in potential energy to come out of kinetic energy. Yeah, so go ahead and solve that yourself. I think I'm done for tonight. Okay. Yeah, just keep in mind that, you kind of have to, when you're changing from one force to the other, you basically got to just, use a different F and different X, right? And K and U at X is equal to 0, right? So then if it's moving in the direction of the positive x-axis, right, you're just doing the exact same thing over here. Just to, again, keep in mind when F and displacement are in different directions. And then at the very end, it says it's released from 0. All right, so if it's released from 0 and going along, right, it picks up some, I think it picks up some, excuse me. it picks up some energy because the potential goes away, and its potential decreases and the kinetic increases. So it's sort of picking up speed along here, and you should be able to figure out what that speed is just from conservation of energy, right? And then it's sort of saying once it gets over here, it starts hitting up against this barrier, and then it eventually stops at some way in, and it's asking you, where does it stop? Yeah. I don't know. I feel like this should be hopefully reasonably intuitive. Maybe I'll just do a little bit of the last example, for part for part K and I, right? So for part K, it's basically just saying, all right, so the initial kinetic is 0, right? Is equal to u1 plus k1. And I guess the idea here is mu1 kind of is this negative thing, so it's going to be like, right, it's going to be whatever this f1 is times, it's going to turn into like minus f1 times 2 minus like f2 times 1, I think it is. So that's going to be for, this is going to be for the potential. And for the kinetic, it's just going to be the opposite of this, right? Because it's got to be equal to 0. So kinetic is equal to the opposite of whatever this thing is. So that tells you what the kinetic energy is. And then you just basically got to figure out how far it's going to go into the other potential, the other forces before it runs out of steam. All right, I think that's all for tonight. Send that there.